So the notes for 21.2a talk about an introduction to normal distributions. So in the notes today, you're going to be looking at data that fit a curve that follows this pattern. So the normal curve's shape shows that over here there's less. Here in the middle is where most of the data is located, and then over here on the right-hand side there's less again. So the height of how far above this horizontal line the curve is going is showing you how much of the data is located in that area. It says that when a data set can be represented by a perfectly symmetric histogram, it can represent a normal distribution. So it's representing 100% of the data. So in a list of numbers, like down here, it's talking about the mass of some different objects that are being weighed. 100% of the data is going to be represented in the histogram, and in some cases in a normal curve. And so we say that the area under the normal curve is 1, indicating that all of the values are being represented. So in this first example, it's helping you think about this idea of 100%. It says that for the frequencies, notice that the pattern is 1, 2, 4, 6, 4, 2, 1. So this would be a perfectly symmetric graph if we tried to create a histogram for it. The bar in the middle would have 6, these two would have 4, these two would have 2, and these two would have 1. So it would be equal on the left and on the right. Let's see. So the first thing that you want to do is go through and figure out in this one how many there are total being represented. So if you go through and add up 1, 2, 4, 6, 4, 2, and 1, and so you sum all of those numbers together, you get that there's a total of 20. So there's 20 values. There's 1 that's 3.3, there's 2 that's 3.4, there are 3 that are 4 that are 3.5, and then it would continue. So relative frequency is found by dividing the frequency by whatever the total is. So if there's 1 out of 20 that have a mass of 3.3, that would be the same as 0.05. So to get this number, I'm just dividing the frequency by the total. So on this table, there's 2 that are missing, so we can figure those out by thinking about the frequencies and the totals. If 6 have a mass of 3.6, it's going to be 6 divided by 20, and typing in 6 divided by 20 on your calculator gives you 0.3. And then if 2 have a mass of 3.8, we would figure out the relative frequency by dividing the frequency by the total. So 2 divided by 20 would give you 0.1 in your calculator. And so what you notice is there's 2 that match up here and here on the outside, and then there's 2 that match up here, 2 that match up here, and then there's 1 in the middle. And so you're going to see that pattern throughout the notes today where it's symmetric on both sides. It says the sum of the relative frequencies is blank. So if I add up this number, this number, this number, and if I go across the row and add all of these up with each other, I get 1 or 1.00 for the sum of my relative frequencies. And so this 1 represents 100% of the data. If you ever add up these relative frequencies and get an answer other than 1, it means that you forgot one of the numbers in the list. So what we're going to be looking at today is in this example down here, it kind of introduces a lesson to you. So if you look at these perfectly symmetric histograms, these bar graphs, where there's the one in the middle that's the tallest, and then it kind of goes down, down, down as you go down the outside, this curve right here doesn't do a good job of approximating the data because it doesn't really fit where the middle of the data is located. But if you look at this second graph right here, this one fits the histogram the best. So we would say that this one was the answer, just put a check mark next to it, that this one's the answer to the question because the curve follows the heights of the bars as they go over time. And so this shape of this curve right here is called the normal curve, and that's what we're going to be looking at in the notes today. So data can be spread out a lot of different ways, but if the data is spread out so that it follows the shape of that curve, we say that it's distributed normally, or that it has a standard normal distribution. Those are the ways that you'll see the word said. And so this is important to remember. It says all normal curves, if they're perfectly normal, they have this pattern for how the data is spread out. So 68 means 68%, 95 means 95%, and then 99.7 means that as a percentage as well. So we did a little bit of an introduction to this when we were practicing finding out how many standard deviations the numbers were away from the mean. So it says here's a standard normal curve. This symbol that's right here in the middle of your graph is it's a Greek symbol. It's pronounced mu, mu, and it means that that's the average of the data. So your mean or your average goes right here in the middle of your normal curve. So the 68, 95, 997 rule says 68% of the data, if it's distributed normally, falls within one standard deviation from the mean. So it's saying that if you measure from your mean, if you measure the standard deviation and you add it on this side and you subtract it for this side, 68% of the data would fall within this region of the graph. So more than half, but less than 3/4 of the data would be located here. So 95 says that if you count 2 standard deviations away from the mean, 95% of the data is located here. So when you see 95%, I want you to think about it meaning like almost all of the data. So almost all of the data would be located here. In fact, there's only this little bit over here and this little bit over here where there would be something else. And then the 997 says that for the last part, if you count 3 standard deviations away from the mean, so you add or subtract the standard deviation 3 times, 1, 2, 3, it says that 99.7% of the data is located from here to here if it's distributed normally. And that, think about 99.7 as being like really almost all of the data, because there would only be like 1 or 2 that are down here and 1 or 2 that are over here that could potentially be like way above or way below the mean. And so we're going to be looking at data sets today that fit this distribution. So they're going to be distributed perfectly normal. And because they're distributed normally, we're going to be able to use this pattern to answer questions about the data.